Hello, everybody. So, yep, I'm Max. I'm the dev rel from NIM. And the talk I'm going to be doing today, which is a mixture of a talk and a demo, is called NIM and Cosmos, an introduction to building privacy-enhanced services. So, if I just... There we go. That's me. I'm Max. I'm the Senior Developer Relations for NIM. And it's basically my job to write all the documentation so other developers can build on it, and then also now build a demo app myself for all of you to have a look at, and look at how easy it is to use our SDK. So the outline of the talk that I'm going to do today, and I've set myself a bit of a challenge by talking about all four of these things, so I'm going to blast through the first two. I've talked about this, other members of the team have talked about this. Those talks are online and they're recorded. Is that good? Sorry? Yep. I'll talk louder as well. So first, I'm going to talk about the problem that NIM is actually trying to solve, which TLDR, it's global surveillance and how to break it. Then I'm going to talk about how the network actually works, so how the mixnet works, our blockchain. Then I'm going to talk about the Rust SDK, which is kind of the main focus of why I'm here today. And then I'm going to show you how easy it is to use the SDK with a demo. And that demo is going to be privacy enhancing a token transaction at the network level, right? So the main problem, which is quite a big one, is with regards to privacy, the internet fundamentally is broken, right? There isn't a single solution right now that can basically defend you, a user, against stuff like people like the NSA. This has been known for a long time after the Snowden revelations. And increasingly, private companies like Google and Meta are able to leverage the massive amounts of compute that they have, and they're able to essentially have like a surveillance dragnet. So they're able to monitor basically most of the internet and use that information in combination with machine learning to start building profiles, building patterns, and start de-anonymizing you and putting you in boxes, right? So you hear a lot about end-to-end encryption. There's a lot of talk about encryption washing at the moment, right? But even if you're using a messaging app like Signal, right, or you're using a zero-knowledge cryptocurrency like Zcash, you're still leaking metadata at the network level. What that means is that you're still leaking information about yourself. You're leaking data about the data, right? You're leaking your IP address, the type of connection you're using, the timing, and all of these things that, again, like I said before, enabled by machine learning, can start building up these patterns about you, and they can start to de-anonymize you, even if the contents of your messages are still encrypted, so they can't be read, right? VPNs don't really help you at all. All they do is push trust. They kind of kick the can down the road. You're sending all your traffic to a VPN, and you're hoping that they either don't get subpoenaed to give a government all the information about their users, and you've probably paid for it using a credit card, or you're just trusting that the VPN isn't actually logging everything and then going to sell that data to someone else, right? So this doesn't help us here. And even Tor can't necessarily protect you against the kind of global adversary that we're talking about here, the kind of adversary that can essentially monitor the whole internet and look at packets traveling around everywhere and tell who is talking to who, right? So that's the kind of lay of the land. That's the situation, which is a huge problem. So the solution that NIM presents is I won't stand in front of it, a decentralized, incentivized mixnet to protect you on the network level, and then a private credentialing scheme, a selective disclosure scheme, so that you can have anonymity on the application level as well. And these are the four components. There is a mixnet. I'm going to talk about that in a moment. There is a token. It's incentivized. We want the people who run the network to be paid for doing so, right? And there's great talks about the tokenomics and how this is working online, our credentialing scheme, and then the Nix blockchain as well. The reason that I'm also at a Cosmos event, we have a blockchain called Nix, which is built with the Cosmos SDK. It's COSM, WASM, and IBC enabled, right? And this is the thing that I'm going to be interacting with later in my demo. But like I said, I've only got 20 minutes. I've set myself a bit of a task, so I'm just going to focus on the stuff that's pertinent for today's talk, right? I'm going to do a high-level overview of how the mixnet works, how this prevents traffic analysis by this kind of global adversary like the NSA that I was talking about, talk about the Nix blockchain, and the Rust SDK, which is what today's demo is built with, and show you how easy it is to use. So how does the mixnet actually help you? What is the mixnet? The goal of a mixnet is basically to create a situation where, even in this situation, where you have someone who has a God's eye view of a network, who can see all the packets moving through the internet, right? Even in that situation, the goal is to be able to create a situation where users can talk to each other, and this global adversary can't tell who is talking to who or when. Which sounds, it sounds simple. It's actually very complicated, obviously. How did we do this? So traffic that's sent through the mixnet goes through multiple hops. I think anyone who's familiar with Tor, it's a similar kind of thing. Packets are routed according to the route that they take through the mixnet. They're decrypted at each hop, and they're sent on, right? This is just a way of unlinking your origin, and your stuff like your IP address from the thing that you're actually talking to, the service you're talking to, right? So they can't tell where the traffic is coming from. All of the data that's sent through the mixnet is encrypted in the Sphinx packet format. It's the same format that Lightning uses. But most importantly, all of the Sphinx packets are the same size, right? So you can start to see how, if you're an adversary looking at the network, then you have traffic going through multiple hops, and all of that traffic looks the same. It looks identical, okay? So stuff like traffic analysis, which you can perform on stuff like Tor, is kind of broken there. All of the traffic that you send is then mixed in with what we call cover traffic, fake traffic, right? So it's mixed in into essentially kind of a constant, imagine a signal being hidden in noise, right? Where the noise is a constant stream of identically sized, identically encrypted packets, okay? And then at each hop, and there's a diagram on the next slide, all of your packets are actually reordered as well. So you kind of send packets to one mix node. That mix node will then hold them for a variable length amount of time. It will kind of mix the packets that it has, and it will send them out in a different order that it got them. Okay? So then you can't follow one of these identically sized packets through the mixnet either. The latency that we currently have is about 500 milliseconds. We're aiming to get that down to about 200 or 300. And we're working on further optimizations on that now, which, if you're interested, come chat to me after. So this is a graph. This was meant to be animated, but it doesn't really matter. So you kind of see at the bottom, with a VPN, all your traffic. It's different sized. You can kind of start to de-anonymize the traffic just based on the timing patterns. Okay. And all you're doing with a VPN, you're kicking it to your VPN, and they're passing it on to whatever service you're talking to. Okay? With Tor, you're doing a similar thing. Okay? Your packets can still be de-anonymized. You can still see the pattern of the packets moving through the network, and they all move through the same circuit, which again doesn't necessarily defend you from an adversary who can watch everything going in and out of the network. Now, at the top, you have you're kind of, before your packets enter the mixnet, they're encrypted to be the same size. There should have been more of them. On the kind of GIF, you can see this. And each of these packets is routed per packet, not per stream, like with Tor, okay? And then they come out the other side. They've all come out in a mixed up order. They're all the same size, and you can't tell exactly where they've come from. I'm blowing through this very quickly because I've only got 11 minutes left, so. If you have questions about this, come find me after. And yeah, here is a more kind of a deeper diagram explaining that and showing how your packets enter your NIM client. They leave it identically sized, identically encrypted. They're all routed individually through the mixnet with the multiple hops mixed in with cover traffic. The timing is obfuscated by the variable length time delays, the mixing. And then they come out of the other side and talk to your service, okay? So that's the mixnet on a very, very high level. Our next chain is a Cosmos SDK-based chain, right? It's Cosm, WASM, and IBC enabled. And this has been running the mixnet since we launched 2 years ago. At the moment, we have 600 nodes. In our test nets, we had up to 10,000 nodes, and it functioned absolutely fine. All of these nodes were actually held, and all the rewards for these nodes were dealt with in a Cosm WASM smart contract as well. So we all kind of know this, but Cosm WASM massively outperforms Ethereum in this regard. There's no way you could have built this smart contract infrastructure on Ethereum, okay? And Cosm WASM obviously is a lot more secure than Solidity and stuff like this. You can't do re-entrancy attacks due to the design of Cosm WASM. Again, whoop, I see some COSM-WASM adherence in the audience. So, onto the stuff that I haven't talked about before, the Rust SDK. We have two SDKs. We have a Rust one and we have a TypeScript one. I'm going to be focusing on the Rust one today. What does the SDK allow you to do? It allows you to integrate a NIM client actually into your code. Okay, so you can deal with the creation of your client, your creation of your key pairs, all of this, and actually integrating the mixnet functionality, so sending your packets, dealing with the stuff that you get back from the mixnet, just into your normal app processes. Okay. Previously, you had to run a client alongside your app. This obviously is quite clunky, it's quite difficult to integrate, so we've kind of allowed for developers to pull this functionality in right now. And even though the SDK is in alpha, we actually rebuilt one of our services, our network requesters, which you can kind of think of analogously to a Tor exit node. We integrated the SDK into that months ago to kind of very, very alpha test it, and those have been running really, really well so far. So even though it's not on Crates.io yet, you can pull it in from GitHub. There's some examples on our documentation of how you can do this. What this actually allows you to do is, as well as the security guarantees of Rust, which are obviously fantastic, you kind of don't necessarily need to worry about all of the complicated mixnet stuff that I just spoke about as a developer. Okay, and I'll show you how easy it is to actually just kind of plug the mixnet functionality into your app now. Obviously, it's good to know, but you don't have to, which is really nice. So, 8 minutes, let's do this. Today's demo is going to be a Cosmos transaction broadcaster service. And so what that actually means is we're going to use the mixnet to privacy enhance a blockchain transaction at the network level. Okay? So we're not going to leak all of that kind of pernicious metadata to the validator that we're talking to, that we're actually kind of giving our transaction to be included in the block. Okay, so we're not going to leak our IP address, the timing, the connection details, any of this, which can be used to de-anonymize you over time, right? We're going to communicate with a service, and that service is going to kind of make the request on our behalf with the mixnet in between us and the service to protect us. Okay, and the bottom of my slides have been cut off, but in the future, you can think about how you could augment the blockchain level either with our own credentialing scheme, our selective disclosure credentials, or any of the other private interchain stuff that's being worked on, right now, which we've seen some of this at the conference today. So the components, we're going to have some client-side code, which is just simple Rust binary, built with the SDK, clap, and some of our validator code, which is also going to be integrated into the SDK very soon. We're going to have the service built with the same thing. And the main thing about the service is that as well as making these requests for us, like on our behalf, on behalf of the client, then the service is actually going to communicate with us, the client, without even knowing who we are, okay? Which is through the magic of something called single-use reply blocks, which I will talk about in a moment. And all we're going to do is going to make a simple token transfer. This is the architecture of it. Our client-side code will run the traffic into the NIM client dealt with in the SDK. That will go through the mixnet to the service, kind of on the other side of the SDK, right? The service doesn't even know who we are. The service will talk to the chain on our behalf, and it will anonymously pass any replies back to us, okay? Oh, if we could have the demo video, please. So we have our service on the bottom, and we have our client on the top. All we're doing is we're calling a transaction, say, sign a transaction offline. We're passing it on a mnemonic, who we want to pay, and then the NIM address, that huge string at the bottom of our service provider. So, as you can see, we're sending the information to the broadcaster, right, saying, could you get the account sequence information for us and the chain ID for our offline signing? And, oh, this is going faster than I thought. It doesn't matter. I will. That's how fast it is, which is nice. It's all right. I've got other slides where I break this down, okay? So let's go back to the slides. Cool. So that's kind of what we're left with, right? And there's two flows of information here, right? That's kind of happening, going from the client through the mixnet to the service and back. So we're going to talk about these first bits now, right? We're going to get sequence information from the chain. Okay, whenever you're signing something offline, you need to have certain bits of sequence information so that you can't, to avoid stuff like replay attacks. So you need to know the sequence, the number of transactions that this account has already made before, and you also need the chain ID. Okay? So this request, the first bit of what we saw there, this request was sent through the mixnet to the service, and the service queried the chain for us. Right? Now, obviously, if I have to tell the if I have to tell the service my address so it can reply to me, then it's kind of useless. You're doxing yourself to a service, right? But through the magic of single-use reply blocks, the service is able to reply to us without even knowing our NIM address. So it's able to reply without knowing who we are. Okay? So even the service can't try and de-anonymize you. How this works is that when your client sends a request to this service and says, hey, could you perform this action for me? Could you query the chain for me? It also sends along a load of pre-addressed packets, right, that the service can write to the payload of. So you're basically kind of sending along a bunch of other packets which are encrypted with the return path through the mixnet to you that the service can't read. But it can write to the payload of. So it can write the responses to these pre-addressed packets and then send them back to you. And that's how we can do anonymous replies. This is kind of what's happening there. So you're basically saying you're constructing a request for sequence information, packaging it up, breaking it up into these identically sized, identically encrypted Sphinx packets, sending it through the mixnet. It goes to the service. The service decrypts those. It deserializes them. It makes the request to the chain. Chain gives it back. And then it's kind of sent with the magic of SERBs back through the mixnet to you, and you deserialize it. Okay? This all sounds very complicated, but it's actually not. And I'll show you how uncomplicated it is now. So this is the code of actually making our client, right? And this is like with the manual storage setup. There is also like a one-liner version of this if you just want to quickly make an ephemeral NIM client and you don't really care about key management and stuff. But this is where, you know, I actually want to properly dictate where the keys live on my machine and all of this kind of stuff, right? Still only like 9 lines of code. So now we look at how we actually construct our sequence requests and send it, right? Our sequence request is just a struct. It's just a simple struct that has the RPC endpoint that we want the service to hit on our behalf, right? Because it's doing this in place of us, remember? From the perspective of the blockchain, the service is the person who's asking for the sequence information. It knows nothing about you, the client, right? And then these lines at the bottom, 18 to 20, which could actually be 1 line of code if they weren't nicely formatted and stuff. All you're doing is you're saying client send string, you're sending it to your service provider, and you're just serializing this message, this request struct, and you're just serializing that so you can send it through the mixnet, right? We're sending a string here. You can also send raw bytes if you want to do that. Okay, so this is now on the service side, and what the service is basically doing is it's listening out on line 29. It's listening out for these requests, and it's going to pass them. And I'll show you like how that happens in a moment. And then from the pass message, what it's doing is it's grabbing 2 things. It's getting the message it just received, and it's getting the sender tag. And what the sender tag is basically a randomized alphanumeric string that just dictates the bucket of these pre-addressed packets that it's going to use to reply to you, right? Because if you imagine a situation where a service is maybe getting, you know, hundreds of requests, it obviously has to be able to differentiate between which SERBs to use to send back to the right people, but it doesn't know the address. So this is just a random UID, basically, for a bucket of SERBs. That's all it is. So we're just passing that, and then we're just sending, right at the bottom, sending a string reply, using these using the SERB bucket, the sender tag, basically to construct like an anonymous recipient type. And then we can use that to send the traffic back through the mixnet. If the clicker was working, then... Oh, no. Oh, here we go. Cool. And this is actually how we're passing it, right? Again, very simple. All we're doing, we get a vector of messages from our client. We pass them into a string, and we just pull out the request type. We pull out that struct, and we pull out the sender tag, this alphanumeric string, and we can use that to essentially do our computation that's requested, and then anonymously reply. So now we're looking at the second bit. Very much the same thing. We're we, the client, we've got the sequence information. We're going to use that to construct. We're going to use that to construct and sign our transaction offline. Yeah? And then we're going to broadcast that signed transaction to the service to make on our behalf. And the service, again, is going to get the response from the blockchain, which in this case is a transaction hash. And it's going to anonymously send that back to us through the mixnet. Okay, so again, this service is making all of these things on our behalf. The blockchain doesn't know anything about us, the client, right? On the metadata level, it doesn't know our IP. It doesn't know where we're coming from. It doesn't know anything about our connection. I'm going to really quickly run through the rest of this now. I'm over time, and basically the same as before. And basically the same as before. So. Oop. I don't know what's happened to my slides. Okay, I'll just ignore those. So this was a very, very simple demo, basically showing how you could use the SDK to kind of protect yourself on the network level, right? Okay, it doesn't matter. Ignore the slides. Yeah, and so obviously, if you were wanting to kind of build this out into an app, if you're wanting to actually protect yourself on the level of the chain as well, then that's where you would have to be thinking about, interacting with either a ZK chain, something like this, one of the kind of private Interchain L1s, or alternatively using our selective disclosure scheme as well, which there is an example of in our SDK documentation as well as our SERP documentation. This is me, Max at nimtech.net, if you want to reach out or just come find me afterwards. This is my Twitter account. Our docs are nimtech.net/docs, and thank you for listening.